Hi everybody and welcome to a new exciting video in the Generating Sound with Neural Networks series. In the last couple of videos we saw how we can move from vanilla autoencoders towards variational autoencoders, but in a kind of theoretical way. Now in this video we're going to take all of that theory and put it into practice so that we can implement a variational autoencoder. Specifically, what I'm going to do is start from the autoencoder class that we built a few videos back, and then using that as a basis to implement a variational autoencoder class. These are the steps that I'm going to go through during this video. First of all, I'm going to modify the graph of the vanilla autoencoder, specifically working with the bottleneck and adding some kind of Gaussian distribution and sampling from a Gaussian distribution, which is the hallmark of a variational autoencoder. Then once we'll be done with that, we'll move on to updating the loss function from the simple reconstruction loss to a combined loss, which also features the Kullback-Leibler loss. Now, I know this is a lot of information, and if you don't have the theoretical background for all of these things, I highly suggest you to go check out my previous two videos. Okay, let's get started now. So the first thing really that I want to do here is just changing the autoencoder name for this class to variational autoencoder. So what I'll do is I replace, and yes, I'm going to replace this. I'm going to replace this, and now I want to change also the docstring accordingly. So VA represents a convolutional variational autoencoder. So let's just write this one here: variational autoencoder architecture with mirrored encoder and decoder components. That's all correct. Now let's move on down here. Now, of course, here we need to replace this, and we'll go down here. Right, and here we'll change this to VAE like that. We can now move to the next step, which is that of disabling eager execution. So the implementation that I'll give you guys for this variational autoencoder doesn't work with eager execution in TensorFlow. Now, if you're wondering about what eager execution is, this is a kind of programming environment that TensorFlow has that enables it to evaluate operations before the graph is completely built. To disable eager execution, the first thing that we need to do is import TensorFlow, and we'll import TensorFlow as TF, and then we can call tf.compat.v1.disable eager execution, and this is as simple as that. Now onto the real stuff. So the first step that we want to implement here, as we said, is the bottleneck, and we need to just change it. So let's take a look at the bottleneck here in the vanilla autoencoder. This is like quite straightforward because we have all the graph for the initial encoder components of the autoencoder, and then we just like flatten it, and then we apply a dense layer that has as many neurons as the dimensionality of our latent space. Okay, so this is like quite straightforward. In the case of the variational autoencoder, this is going to be slightly different. And specifically, what we are going to be doing here is we want to sample a point from our Gaussian distribution. And so for doing that, we need three things. So the first one is a min vector, then we need a variance vector, and then we need this epsilon, but we'll see this in a second. But for now, let's just focus on the Gaussian distribution itself and on its two main parameters, right? So the min vector and the variance. So we want to implement these two things. So for doing that, what we can do and what we will do is having a couple of dense layers, one for the min vector and the other one representing the variance, specifically the log variance. So let's do that. So we'll create a new attribute called self.mu, and this will represent the min vector, and so we can say dense, and the dimensionality of our min vector is going to be equal to the dimensionality of the latent space. So we'll do a self dot latent space dimension, and then we'll pass in the name, and the name here, not surprisingly, is going to be moo. Okay, of course we have this dense layer and we need to apply it to the graph we've built so far. So we'll do this parenthesis x. Okay, now let's move on and do the same thing for the log variance. And once again, we are going to have another dense layer whose dimensionality is going to be equal to the dimensionality of the latent space, right? So, or dimensionality for the dense layer, well, I mean just like the number of neurons here, right? So we'll do self dot latent space dimension, which stands for dimension, of course. And then the name here is going to be equal to log variance. Okay, and once again, we need to apply this new dense layer to the graph. And as you can see here, for the first time, we don't have a sequential graph anymore, right? Because we take the graph that we've built so far, and then we branch it out into two dense layers. The one which is the one representing the min vector, and the other one representing the log variance. So we just branched out. Okay, now the next step will be that of sampling a data point from this Gaussian distribution that is parameterized through like this mu dense layer and the log variance dense layer. So how can we do that? Well, we need a function that samples a point on the Gaussian distribution for us. And we need to wrap that function within our graph. So how can we do that? Well, Keras can help us with an amazing layer called the lambda layer. So a lambda layer is used in Keras for wrapping functions within our graph. So let's do that. So we can say x, which is going to be our graph. And here what we want to do is apply a lambda layer. Now, of course, we haven't imported the lambda layer because this is the first time that we've seen it. So let's do that in a second. So we'll go up here in this import statement here with the layers, and we'll import lambda like that. Okay. So now we have this lambda layer. The lambda layer, as you can see, as a first argument takes a function. This is like the function that we want to apply to our data and wrapping it into like our lambda layer. So we need a function, and for now I'll just call this sample point from normal distribution. Okay, so this is going to be the long name of our function, which of course we haven't defined yet, and we'll define it in a second. Now, the next thing, once again, we want to provide a name to this layer, and the name in this case is going to be encoder output, because this is actually going to be the output of the encoder, right? And this is the point where the two now separated part of the graph. So the dense layer for mu and the dense layer for the log variance are going to kind of going to converge together once again. And indeed, what we need to pass here is both of those parts of the graph. So self.mu and self.log variance. And we'll do that like this, self.mu and self.log variance. Okay. So now, okay, let me just like bring up this. Okay. Now, what we should do actually is defining this function called sample point from normal distribution, and we'll define it as an inner Python function. So this is a function within a function, or a method within a method, if you will. Okay, so we'll define it up here, and this function is going to get as an argument a kind of like generic argument called args, and these args is basically whatever we pass here in the lambda layer, okay? So the first thing that we want to do is just like get whatever like we passed in the lambda layer, and we know that we're passing mu and log variance. So we'll do not that, mu and log variance, and this is going to be equal to args. Okay, so now what we need to do is get all the different parts of this equation in place. Now we have mu, which is this min vector. We have the variance in the form of log variance, and we'll need to do a little bit of a transformation there, but we'll see that in a second. What's still missing is epsilon. Now, what's epsilon? Well, we already saw this in the previous videos, but epsilon is a sampled point from a standard normal distribution. So we sample point from a standard normal distribution, and then we apply mu and we apply sigma to it. And what happens is that at that point, basically, we are getting a point, sampling a point from our Gaussian distribution defined by our mu and log variance dense layers. Okay, all of this to say that we need to get epsilon. So how do we do that? Well, that is quite straightforward, because we can use the Keras backend. So Keras backend has a lot of juicy functions for us, and one of which is random normal, which is a nice normal distribution. So here, what we want to do is we want to sample a point from this normal distribution. First of all, we need to pass the shape. So how many dimensions we have in our normal distribution. Of course, the dimensionality of this normal distribution should be equal to the number of dimensions that we have in our latent space, right? And so we can do shape, and we take the shape, and once again, using the Keras backend, we can take the shape of self dot mu, and then we need to define another couple of parameters, one being min. The min, this is like the min of the this multivariate normal distribution, and given we want a standard normal distribution, we should put the min equal to 0. So we'll do a 0 here, and then oops, comma, and we need to pass in the standard deviation, which in the case of a standard normal distribution is equal to 1. So as you might have seen earlier from the suggestions from PyCharm, so the default for this random normal function from the Keras backend is the parameters for min and standard deviation are 0 and 1 respectively, which are the ones that we use for a standard normal distribution. But I just want to have them there, so that it's going to become very, very clear that we are dealing with a standard normal distribution. Okay, so now we have sampled a point from the standard normal distribution. What remains to be done is actually doing this. So kind of like implementing this simple equation here, and then we'll get this z, which is our sample point. So sampled point is equal to mu plus sigma. Now, what's this sigma? Well, sigma is this thingy here. Now, what we have is the log variance, which is this. And so to get to sigma, we need to apply the exponential to our log variance. So how can we do that? Once again, the Keras backend is going to have our back covered. So we'll do k.exp will pass the we have the log variance here, and then we should divide by 2 if I remember correctly. Yes. Okay. So now we have our sigma, and the last thing that remains to be done is a multiplication with epsilon. And so here we have our sample point, and we can return the sampled point, and I believe we should be done with the bottleneck. Now, one thing that I want to modify from this is just this doc string here. So we don't just flatten data and add bottleneck. We actually flatten data and add a bottleneck with Gaussian sampling like this. Okay. Nice. So everything should be in place here with this add bottleneck. So we have this enhanced version of the bottleneck with Gaussian sampling. So our first step here is done. So we can move on to the second step, which is that of updating our loss function. And we're going to be building our own custom loss functions for that. And so the first thing that we'll be doing is creating the reconstruction loss, which is just a simple MSE, min squared error, and then we'll build KL loss, and finally we'll combine this in another method that we'll call, combined loss. Okay, so now where should we do all of those things? Well, I suggest we do it here just below this class method where we start having private methods down here. Okay, so the first thing we said we want to have the let's call it calculate reconstruction loss. Okay, now this is going to be a custom implementation of a loss function in Keras, and for those type of functions, what Keras expects from us is the so-called y target, which is the output target, and y predicted, which is the output that has been predicted by the about our model, right? So we need these two elements and pass them to have a custom Keras loss function. Let's implement the error first. So the error is given by y target minus y predicted. Okay, now we want the reconstruction loss. Okay, so how do we go about this? Well, we want to actually implement min squared error. So first of all, we are going to square the error. So how can we square the error? Well, once again, let's rely on our old friend, capital K, the Keras backend, which is going to give us this square function. We'll pass in the error. And so all of a sudden we have a squared error here. That's great. Okay, so what next? Well, we need to take the min of the squared error. So let's reuse the Keras backend, which luckily for us has a min function, and then we'll pass in the square error. And here we need to specify on which axis we want to take the min, and these are going to be axis 1, 2, and 3. Okay, so we can happily return the reconstruction loss now, and we are done with the first part of the loss update. So now, second part, KL loss. So the Kullback-Leibler divergence, which we'll be using for calculating a loss. So we'll do a define calculate KL loss like this, and so we'll pass once again y target, y predicted, and down here we need to actually start building the all the expressions that we need to get the KL loss. Let me refresh you about the Kullback-Leibler divergence. This is something that we can use to calculate the difference between two distributions. In our case, we are going to be using the closed form, where we want to calculate the difference between our Gaussian distribution from the standard multivariate normal distribution. Now, why do we want to do that? Well, we want to do that to use that distance, if you will, as a loss, because we want to pull our Gaussian distribution towards the standard Gaussian distribution. Okay, so if you want more details about all of this, once again, just go back to the previous videos in the series and you'll find all the details about that. Okay, so we have this expression here that we need to implement, and actually we have to take minus here because we want to take it as a loss. Right, so we'll do a minus 0.5. Let's do it like this, and then we'll multiply the sum here. So the sum of all of these things. So the sum, once again, can be performed relying on the Keras backend. So we'll do a sum here, and here we need to pass all of these variables or arguments. So 1 plus the log variance that we already have. So we can do a self.log variance, very easy peasy like that. And then minus, we have to square the min vector. And so we'll do a k.square, and we'll pass self.mu. And I believe we should do a minus and the variance here. So how do we get the variance from the log variance? Well, we have to apply the exponential to the log variance. So we'll do a k dot exponential, and we'll pass in self.log variance like that. Okay, let me just double check if everything is right here. So we have 0.5, and we have like this sum where we have 1, the self-log variance, the square of the min vector, and finally we have the variance. That's great. Okay, now we have to specify on which axis we want to do this sum, and we'll do it on the axis 1. Okay, so we have the KL loss now, and we can happily return it. So we'll do a return KL loss like that. Now you may be wondering, but Valeria, why did you pass these y target and y predicted, these two arguments, if you're not using them? Well, that's because we are defining a Keras loss, custom Keras loss function, and in the Keras framework, so Keras is expecting for custom loss functions to have y target and y predicted as arguments. So this is the reason. Now, the final thing for updating our loss will be that of creating a method that will enable us to combine these two losses, so the reconstruction and the KL losses. Okay, so we'll do a calculate combined loss. Now, what we need to pass once again is y target and y predicted. And now what we need is the reconstruction loss, and we can get it by calling self._calculate reconstruction loss and passing y target and y predicted. Then we need to get the KL loss, and this is also quite straightforward to get through our private method calculate KL loss, and we'll pass in once again y target and y predicted. And now we have the combined loss. And so how do we define the combined loss? Well, this is once again something quite easy. And if you guys remember from my previous video, so this combined loss is given simply by the sum of the reconstruction loss and the Kullback-Leibler loss. So we take the reconstruction loss and we add up the KL loss. You may think we are done, but actually we're not. There's still one little aspect to add to what we have here, and it's this one. So we need to weight the loss function. Specifically, we want to weight the reconstruction loss over here. So how can we achieve that? Well, that is easily done by adding a new attribute, which we'll call reconstruction loss weight, and we'll just multiply the reconstruction loss weight by the reconstruction loss. Of course, this hasn't been defined anywhere, so we need to define it, and we can define it up here in the constructor, and we'll give it for now a value of 1000, which should work for this specific use case. Okay, and now let's go back down here, and all that remains to do is to return the combined loss. Okay, so now we are done with updating losses, because as you can see, we have these 3 new super nice private methods. We have the calculate combined loss, which relies on these 2 others methods, so calculating the reconstruction loss as well as calculating the Kullback-Leibler loss. Okay, now of course, we implemented this, but we have to use them. Otherwise, yeah, they're completely useless, right? And so where should we use them? Where should we put them? Well, we should put them in at the moment where we compile the Keras model. Up here in self.model.compile, you can see that we are at the moment passing MSE loss, which is our reconstruction loss. And but we can just like delete that part, and here for the loss we can, or we should, pass self.calculate combined loss. So we pass this method here, and then we also want to pass metrics. So we are going to pass a couple of this so that we can see these different losses while we are doing while we are in the process of training. So what are these two metrics? Well, of course, it's the reconstruction loss and the KL loss. So we'll do a self.reconstruction. No, it's a private one. So we'll do calculate reconstruction loss is one, and then the other one is self.calculate KL loss. Okay, good. I think we should be done now with all of the updates for getting to a VAE instead of just having a vanilla autoencoder. Now, one thing that I want to do is just quickly running this to see the architecture and see like if everything works as it's supposed to do. So let's run this script. Hopefully we don't get any errors. Wow, seems like it's working. So here we're gonna get like the whole autoencoder with its encoder parts, encoder input, the encoder and the decoder, but I'm not interested in that. I'm not interested in the specifics of the decoder. What I'm interested in is the encoder parts, and specifically towards the end of it, after like this flattened layer, we have the two layers, right? So the min vector layer and the log variance vector layers, which get as input flatten both of them, which is nice, and their dimensionality like is equal like to 2, which is expected because we are passing only like 2 as the latent space dimension. And finally, for the encoder output, we have once again like dimensionality equal to 2, and the input for this is both the mu dense layer and the log variance dense layer, which is what we expected. So all good, everything is working correctly. That's great. Now, what we want to do next? Well, we want just like to try this out and train this variational autoencoder with the MNIST dataset that we have, or a subset of that, and then we want to generate new digits. Now, let's go in the train.py. I think like here we have to change a few things. Like here we have this autoencoder class that we're importing that no longer exists. So we need to change it to VAE over there. Same thing down here, VAE. And the rest should work as is. Now, just one thing, of course, like to be more precise, you should change all of these autoencoder variables to VAE, but yeah, I'll just leave it to you. This is a minor thing, really. Okay, so now the final thing for this training part is just running the script. I think this is going to take a little bit of time because I'm doing 100 epochs. So I'll just like start the training, and then probably I'll post the video and see you in a second after it's done. Okay, so here we are starting. It seems like it's working. And as you can see here, we have the loss. That is like our combined loss. But here we can also see the reconstruction loss as well as the KL loss, if PyCharm allows me to do it. Okay, so you can also see the KL loss there for each epoch. Okay, so now I'm just gonna stop the video here and reprise it the moment this is ready. Training is now finalized, so we can move to the final part of this video, which is just seeing the results of the training of this new variational autoencoder for generation. So we have another script that we built a few videos back in the series, which is called analysis.py. And now I want to run this. So first of all, of course, I have to change this import, and instead of autoencoder, I'll import VAE, and probably we need to change this one as well. Yes, so we'll load from VAE, not autoencoder anymore. And let me run this, and so we'll see an example of generated digits compared to the original ones, and then we'll see the latent space representation and see how, and we can compare it against like what we had a few videos back when we did the same thing but for vanilla autoencoders. So let's do this. Let's run this analysis. So hopefully everything will go well. Here's the result of a generation. On the upper row you have the original digits, and on the row below you have the reconstruction which went through the variational autoencoder. So they do the variational autoencoder does a pretty good job, but there are a few issues. For example, this 2 is not really a 2. To me, it's super blurry. If anything, I would say it's an 8, but yeah. But this is absolutely to be expected, because at the end of the day, we only used 2 as the dimensionality for the latent space, which is like really, really small. If you were to put like a 16 or like 24 or something more than that, it would be like very, very good, the quality of these reconstructions. Now let's move on to why we actually use just like 2 dimensions for the latent space, which was for doing this analysis. Here we have the representation of the latent space, and as you can see, it is more or less centered around the origin, so it's 0, 0, and this was to be expected because we actually implemented the Kullback-Leibler divergence and error just for having that result. So what the KL loss did was pulling the distribution towards the center. Now, the other aspect that is important that we have here, which is kind of different from what we used to have with the same latent space representation, but for vanilla autoencoder, is the fact that the dots are distributed in almost like a continuous way. There aren't many subspaces of this space where you have like just like blank spaces, right? And this is very important because that means that you can generate things that are more or less meaningful. And if you just like move a little bit far away from a dot, you wouldn't expect something that's completely not meaningful, but actually it should be meaningful, and it should be more or less close to the dots that you have as a reference there. So yeah, it seems that the VAE works as it was supposed to do. So now what remains to be done in this series is actually moving from this simple generation of digits towards generation of sound. So how are we going to do that? Well, you'll see that in the coming videos. So yeah, stay tuned for moving on to the final leg of this wonderful journey about like variational autoencoders for generating images and sound, and you'll see how that's done. So that's all for today. I hope you enjoyed the video. I hope you found it useful. If that's the case, please leave a like. If you're not a subscriber of the Sound of AI channel, please do subscribe and hit the notification bell so you'll continuously get all of these videos updates regarding like my activity. So that's all. I'll see you next time. Take care. Bye.